Good afternoon class. My name is Abhishek Gupta and today I will discuss one of the topics on phase diagram. This phase diagram actually comes under the unit 1 of the subject material science. These are the contents today which we will study about. First is we will study the basic terms which are involved in the phase diagram. Then what are the difference between component and phases? What are the phase solutions? Then what are the solid solution and what are the intermediate alloys are generally used in forming any component. Then what are the non-homogeneous phases and mechanical mixtures. Then moving furtherwards, we will study the Rothe rule, which is used for solid solution when we have to join two different metals and form a compound. After that, we will study the different solidification methods, Gibbs phase rule, equilibrium phase diagram. Equilibrium phase diagram is actually divided into two types. One is the unary phase diagram and second is the binary phase diagram. Then in the middle, we will discuss about the cooling curves, which is generally seen how the material has been cooled from higher temperature to lower temperature for a particular time interval. And then in the ends, we will study about the lever arm principle. So some of the basic terms which we generally study before studying the phase diagram is, first is the system. So system, you already know that in thermodynamics a system is an isolated body of matter which is under consideration for study. So a substance or a group of substance so isolated from its surrounding that it is totally unaffected by the surrounding, but overall changes in its overall compositions, temperature, pressure or total volume can be allowed as per the desire of the persons. So actually system is any that concentration area on which our whole focus is focused. A system can contain solid, liquid or gases or their combinations. It may have the metals and non-metals separately or in the combined form. Then coming on to the phases, a phase is a substance or a portion of matter that is homogeneous, physically distinct and mechanically separable. Physically distinct or mechanically separable means that the phases will have a definite boundary surfaces. There are different types of phases which we generally see, like alpha phase, beta phase, gamma phase, and depending upon the types of state also, phases can be differentiated in terms of solid phase, liquid phase and gaseous phase. So here you can see that this is the structure showing the system, and here silica rich phases is there in borate rich phases, which includes finely dispersed silica. Then coming on to the what are the components. Components are actually the pure metals and or the compounds of which an alloy is generally composed of. For example, copper and zinc materials is used in order to form the brass. So in brass, generally copper and zinc, these two materials are used. Then it refers to the independent chemical species. The component of the system may be it can be the elements, ions or the compounds. So you can say that a component can exist in many phases. For example, in water exists in ice, solid phase, liquid phase and water vapor phase, whereas the carbon exists in the graphite phase or the diamond phase. Then the component, how you will define the component. The component can be defined that element or compounds that are mixed initially, like aluminum and copper. Whereas the phases, we have already discussed that phases is an homogeneous, physically distinct and mechanically separable portion of the material with a given chemical composition and structure. So studying further, we will study about the equilibrium of the system. So equilibrium of the system is the minimum free energy under any specified combination of overall composition, temperature and pressure. Once equilibrium is achieved, then even a minor change in the parameters of composition, temperature and pressure increases the free energy of that system. So next topic is the degree of freedom. Degree of freedom actually denotes the variance of the system. It defines the number of external or internal factors of the systems which can be independently changed. Whenever we independently change these systems, then it doesn't affect the equilibrium of the system. so without causing disappearance of a phase or the formation of the new phase in the system. Then fifth topic is the structural constituents. Phase distribution in a system is not necessarily uniform throughout the structure. These phases are associated in different ways to form the structure. This association of phases in a recognizably distinct fashion is referred to as the structural constituent of an alloy. Then there are different types of single solids or multi-phase solids. A single crystal of a material may consist of one phase only, while the polycrystalline materials may be a single or multi-phase depending upon the nature of the individual crystals or the grain present. So all pure metals are generally the single phase solids, and alloys like iron and steel, rocks, ceramics, woods, fiber, glass, polymers are the examples of multi-phase solids. There are various properties of multi-phase solids which depends upon the physical and chemical nature of the phases present, and it also depends upon the what amount of phases these amounts are actually present on the component. Then it also depends upon the distribution of each phases and their relationship with other phase, and it's also depend upon the size of the domain occupied by the each phase. Then next topic is the alloy. As you already know that the alloy is the combination of two different materials. Generally every metals have their their physical quantity and mechanical properties, but in order to enhance the mechanical properties and physical properties, we generally use two different types of material, and these two different types of material when clubbed together it form the alloys. So by using the two different types of material in a single in order to form the alloy, we actually utilize the properties of both the materials, and these type of materials can be used on a particular applications. So a metal present in the larger proportion is called the base metal, while the other metallic or non-metallic element which is present in the lower amount, then that type of element is known as the alloying elements. So elements may combine in different ways in order to form the alloys, and these elements of alloys usually show complete solubility in liquid state. However, on cooling them to solid state, they may form mechanical mixtures or homogeneous phases. So what is a solution? Solution is a phase with more than one component and a mixture of material with more than one phases. So solute is the minor component in a solution which does not change the structural pattern of the solvent, and the composition of the solution can be varied. In mixture there are different phases, each with its own atomic arrangement. It is possible to have a mixture of two different solutions. So for many alloy system and at some specific temperature, there is a maximum concentration of solute atom that may dissolve in the solvent to form a solid solution, and this is called a solubility limit. So solid solution cannot have a formula, so these are indicated by the Greek letter like alpha, beta and gamma. The addition of solute in excess of this solubility limit results in the formation of another solid solution or the compound that has distinctively different compositions. So here you can see that a graph is made between the temperature and the composition. We are adding a sugar in the water. So here the sugar content is going to increase, and here and in this manner water content is going to increase. So when you draw the graph between the temperature and the weight composition, then you will see that this type of graph is generally shown, and this red color graph actually shows the solubility limit of sugar in water, and here it shows the liquid solid syrup, and here it shows the liquid solution plus solid sugar. So phases can be classified either in homogeneous phase or non-homogeneous phase. Homogeneous phase are further classified into solid solution and intermediate alloy phases. Actually solid solution means two metals mix within the solubility limit, then that type of solution is known as solid solution. Whereas two metals mixed beyond the solubility limit, then that type of phases are known as intermediate alloyed phases. Then this is further divided into substitutional solution, so interstitial solid solution, and intermediate alloy phases are further divided into intermediate solid solution and intermediate compounds. So you can see that This is the whole classification of phases in homogeneous phases and non-homogeneous phases. Then homogeneous phases are those phases when two elements are completely soluble when coming into solid state from a liquid state and forms compound by chemical reactions. They form phases known as homogeneous phases. Each component of such phases loses its own identity, properties and crystal structures. So coming on to the solid solution when two elements completely mix or dissolve in each other in liquid as well as solid state during the process of solidification, then the resulting structure or the phases is known as solid solution. In a solid solution, there can be more than two components, but in general, the metal which is in the higher proportion is known as the base metal, and the that alloying element which is present in the very little quantity, then that type of material is known as solute or the alloying element. So there are two different types of solid solution. One is the substitutional solid solution and another is the interstitial solid solution. So substitutional solid solution, you can see here that when an external solute like copper comes in between these solvent like nickel. So you can see this is the copper, one copper, and these four are the nickel. So in the interstitial sites, nickel copper atoms take place of interstitial sites in between these solvents, nickel solvents. Whereas in a interstitial solid solution, this is the interstitial space, and substitutional solid solution, one copper atom replaces one nickel atom and forms this substitutional solid solution. Similarly, there are disordered substitutional solid solution and ordered substitutional solid solution. So you can see that here ordered in an orderly manner, these atoms are arranged, whereas here there is no specific order in which different types of atoms are arranged in disordered substitutional solid solution. So there is one rule known as Rothe rule for solid solution. Two materials whenever combine together and form an alloy, there is some rule which has to be followed. Otherwise, if these rules are not followed, then we can say that these two different materials can't combine. So first condition is that it depends that what is the crystal structure factor, what is the relative size factor, and what are the chemical affinity factor, and in the last what is the relative valence factor. So critical structure factor of two materials should be same in order to form the alloy. So this is one of the important condition in order to form the alloy, that their crystal structure factor should be same. Second is that the relative size factor should be considerable, that the two atoms, that the two materials which we are going to join and forming an alloy, then their atomic size difference should not be greater than 15%. It should be less than 15%. Then only we can say that the two elements can form an alloy. And so you can see that the percentage difference should be less than 15%. Then third factor is the chemical affinity factor, that greater the chemical affinity of the two materials, the more restricted their solubility in the solid solubility. So when their chemical affinity of the two material is great, the metal tends to form an intermediate phase rather than the solid solution. Generally, the farther apart the elements are in the periodic table, greater is the chemical affinity. If the elements have similar electronegativity, they will make a solid solution. And if the elements have similar electron negativity, they will make a solid solution. Same line repeated. Electronegativity and electron affinity of both the material should be same. Electronegativity and electron affinity. Electron affinity means the same element attracts its one electron toward itself, whereas an electronegativity means different atoms, different elements, atom attract different one element attracts different electrons of different atoms. So this should be comparable, then only an alloy can be formed. Then the fourth is the relative valence factor, that the valency of both the materials should be same, otherwise these alloy system cannot be formed according to the Rothe rule. Then next we will study about the Gibbs phase rule. Gibbs phase rule actually establishes the relationship between the degree of freedom, number of components, and the number of phases which are actually present in a solution. So Gibbs phase rule gives this mathematical terms, that is P plus F is equal to C plus 2, whereas P is the number of phases. It can be solid phase, liquid phase, or etc. And F is the degree of freedom or the number of physical variables like pressure, temperature, or concentration that can be independently changed without altering the equilibrium, that is without causing the disappearance of a phase or a formation of new phase in the system. So you can see that there are three different variables: pressure, temperature, and concentration. So C is the number of components in the system. For example, lead and tin are the components of a lead and tin equilibrium diagram. So Gibbs phase rule here, provided the equilibrium between any two of the phases is not influenced by the gravity or the electrical forces or magnetic forces or surface tension, and influenced only by the temperature, pressure, and concentration, then the number of degree of freedom of a system is related to the number of components and the number of phases with this equations. In studying the equilibrium, chemical equilibrium, temperature and pressures are considered as the external factors which are determining the state of the systems. Therefore, in the phase rule equation, the digit 2 stands for the two variables. One variable is temperature and another variable is pressure. In applying the Gibbs phase rule to the metal system, the pressure is considered as the remaining fixed parameter. Therefore, the effect of the pressure is neglected, leaving only one variable factor, that is temperature. So whenever you take only one factor, then the Gibbs phase rule changes its form, and the degree of freedom can be calculated with the help of F equal to C minus P plus 1. Whereas in place of 2, it comes 1, because here only one factor at a time has been taken, that is temperature, not the pressure. So since the degree of freedom cannot be less than 0, so if you will do it, so C plus 1 minus P should be greater than 0, then P should be less than or equal to C plus 1, which means that the number of phases cannot exceed the number of the components plus 1. So phase diagram, we have already seen that the phase diagram are important and essential tool to understand the compositional concentration of the two or the more elements. Phase diagram is actually drawn between the temperature and the chemical composition of the elements. So for unary phase diagram, number of components should be 1, and for binary phase diagram, number of components should be 2. Phase diagram also shows the melting point of an alloy. So with the help of phase diagram, we can also find out the melting point of the alloy. So equilibrium phase diagram is the diagram that depicts the existence of different phases of system under equilibrium, and this type of diagram is known as the phase diagram. It is actually a collection of solubility limit curves. It is also known as equilibrium or constitutional diagram. Equilibrium phase diagram represents their relationship between temperature, composition, and the quantities of phases at equilibrium. These diagrams do not indicate the dynamics when one phase transforms into the another. So it shows the phases present at different compositions and the temperature under slow cooling. It indicates the equilibrium solid solubility of one element component into the other compound in another. It suggests temperature at which an alloy starts to solidify and the ranges of solidifications, and it signals the temperature at which different phases starts to melt, and the amount of each phases in a two-phase mixture can also be obtained. So coming on to the unary phase diagram, this is the unary phase diagram for water. So you can see that there is one triple point at which all liquid, water, and ice coexist. So generally unary phase diagram is drawn for the most pure form of elements like water, or you can say carbon. Then this is the cooling curve. Cooling curve is actually drawn between the temperature axis and the time axis, and there is a method to determine the temperature at which the phase changes occurs from liquid to the solids in any alloying systems. So you can see that the temperature, how the temperature is varying with respect to the time for the pure metals, or for the binary solid solution, or from the binary eutectic systems. So you can see that how the temperature is decreasing with increasing in time, and there is some same temperature, constant temperature for a particular interval of time, then afterwards the temperature starts to decrease as the time moves on towards. So cooling curves of pure metals or compound can be seen here. The liquid metals cools from P to Q. First crystal begin to form at the point Q, and from point Q to R, the melting liberates the latent heat of fusion in such an amount that the temperature from Q to R remains constant until whole mass is entirely solidified at point R. And between Q and R, the mass is partially liquid and partially solid. On further cooling from R to S, the solid metals cools and tends to reach to their room temperature. The slope PQ and RS lines depends upon the specific heat of liquid and the solid metals. This is the cooling curve for binary to actic, you can say. In binary to actic, two components are present. This is the binary phase diagram. Binary phase diagram is made between nickel and the copper. So you can see temperature and time axis is there. On moving forward, we see that the nickel percentage is decreasing and the copper percentage is increasing. So you can see that this is the two curve is generally obtained. This upper curve is known as liquidus curve, and this lower curve actually shows the solidus curve, and in between these it shows the mushy zones. And and whenever you draw one vertical lines, it actually shows the cooling curves or the for this phase diagram. So two component systems are classified based upon the extent of mutual solubility and are completely soluble in both liquid and solid phase. So binary phase diagram, you can see that there is one tie line. This tie line, there is one alloying composition. When you draw one vertical line, then this vertical line actually shows the alloying one alloy. So you can see that this point is the solid point and liquid point. Beyond this point, everything is liquid, and beyond this curve, everything is solid. So that's this line which separate liquid region to the mushy zone is known as liquidus region, and the line and the curve which separates solid region to the mushy zone is the solidus region. So you can see here that on x-axis bismuth percentage is increasing, and on moving forward we see that the antimony percentage is decreasing. So this is the lever arm rule, in which the proportion of coexisting phases at given temperature has been drawn, and you can see that these are the lines. This is the first line point, this is the second point, this is the third point. First point lies in liquid phase, third point lies in solid phase, and the second point lies in mushy zone. So whenever you take this point and draw one horizontal and vertical line, and take this point and draw vertical and horizontal line, then this point actually shows the percentage of solid fractions, and this point shows the percentage of liquid fractions. And any point say here, when you draw some vertical lines, then this point shows the overall compositions. So with the help of this tie line, you can actually find out the percentage of mass fraction of liquid present in the alloy system, and the mass percentage of solid present in the alloying systems. So in the further study, we will study how the mass percentage or the fractional percentage has been find out between these two components. So a lever arm rule actually shows the intersection of this composition vertical line AL and a given isotherm line OP. So OP is the isotherm line, that is M is the fulcrum of a simple lever system, and OM and MP are the two levers. OM and MP are the two levers. If one person sits here and one person sits here, the person which is heavy comes down, and the person where weight is low, it goes up. So in order to find out the mass fraction of the solid, so you will take this distance upon total distance, and in order to find the mass percentage of liquid, you take this distance upon the total distance. So the relative length of the lever arm multiplied by the amount of the phases present must be balanced. This is called the lever rule, because the amount of a given phase multiplied by its lever arm is equal to the amount of other phase multiplied by other lever arm. So you can see here that in order to see how this lever arm principle works, it can also be seen that the proportion of the solid corresponding to the length of the segment adjacent to the liquidus lines, whereas the fraction of the solids corresponding to the length of the segment adjacent to the solidus line. So you can say here liquid plus solid, both region exist, whereas here liquid exists and here solid exists. So this isotherm line OMP can be considered as the tie line, and since it's joined the composition of two phases, one phase is the solid phase and other phase is the liquid phase. And in order to find out the amount of solid phase, so solid is present here. So in order to find out the amount of solid phase, you will take the distance from fulcrum to the other point divided by the total distance. So you will take MP upon OP in order to find out the mass of the solid phase, and in order to find out the mass of the liquid phase, you will take the distance between overall composition to the solid composition divided by the total distance, that is OP. So in order to find out the amount of the liquid phase, you should take OM upon OP into 100. So MP is 62 minus 30 and OP is 62 minus 14 into 100. Then the amount of solid phase, which actually comes, is around 66 into 2/3%, whereas the amount of liquid phase actually shows OM upon OP. OM upon OP. OM means 30 minus 14 upon OP is 62 minus 14 into 100. Then it comes around 33 into 1/3%. So by these equations, you can actually find out the amount of solid phase and the amount of liquid phase present in any component or the alloy. Thank you, class.